Hello. In today's video, we're talking about context engineering. Context engineering is a term that's kind of floating around on the internet recently, and it has to do with how you create LLM applications. According to Andre Karpathy himself, context engineering is this subtle, delicate art of fitting information into the context window of an LLM before you ask it to do a task. So it's not just prompt engineering where you create one prompt to make the LLM output a single thing. Instead, it's about that whole ecosystem where you break up your task into sub-problems, you connect them together with control flows, you pack the information into the LLM correctly, and that information source can come from anywhere. It can come through tool calls or RAGs or news sources or even from few short examples that you added. And on top of that, there's also the consideration of guardrails, evaluation, memory, prefetching, caching, everything that makes your LLM applications run, they all come under this umbrella term of context engineering. Now, you might be wondering, bro, I've seen LLMs with context windows up to 1 million tokens. Why can't we just fit everything in there and the LLM's going to do its job? Well, this doesn't work. There's a lot of research that indicate that LLMs can suffer through something called as context poisoning, where if you include too much unnecessary details into the LLM's context, it begins to pollute the overall understanding of the LLM, and that results to poor performance where it starts hallucinating or it starts picking up patterns which are not really relevant to answer specific queries. In this video, I'm going to walk you through the main ideas behind context engineering, the main building blocks with which you can go from simple atomic prompt engineering into building large-scale applications with multiple agents, proper evaluation systems, and guardrails. This tutorial is going to be using Python and DSPy. If you don't know about DSPy, it's a prompt programming framework that allows you to generate structured outputs, and it contains modules that already do a lot of heavy lifting to implement some of the features that we're going to talk about today. Frankly, if I was not using DSPy for this tutorial and I was just writing prompts in plain English, this tutorial is going to be way bigger. A lot of research has gone into producing this video, and I'm very proud of the outcome that I have been able to achieve. My goal in this video is to be as comprehensive as I can in all of the topics that I'm going to cover, and I hope you find a lot of value in this. As an example, I'm going to use joke generation, and by the end of this video, there's going to be some really insane jokes that these LLMs are going to be generating. This tutorial is divided into 5 sections. First, we're going to talk about the basics of prompt engineering, how to write atomic prompts, and we're going to do a simple introduction of DSPy. In the second section, we're going to have a look at more complicated examples with multi-agent interactions and multi-step prompts. The third section, we are going to look at some ways to evaluate code and have observability into what your LLM applications is actually doing. In the fourth section, we are going to be discussing tool calls. And in the fifth section, we are going to be discussing Retrieval-Augmented Generation or RAG. Also, throughout this video, I'm going to take a single simple example and build upon it by introducing all of these concepts one by one so that it gets easier for you to understand how each of these components really add to the overall flavor of one project. And additionally, I'm also going to be including some simple ways to evaluate, unit test, and add guardrails to each of these sections. So make sure you don't skip those parts. Most of this tutorial is going to be open source, so I'm going to keep a GitHub link in the description below. So go check it out if you want to follow along. If you're a member of my Patreon, you'll also get access to all of the slides, documents, as well as some additional code materials that I've prepared just for you. These are all of the amazing people that support me on my Patreon every month. I'm eternally thankful for your confidence. I just reached 20,000 subscribers on YouTube and 500,000 views. That is amazing. I thank you a lot. You guys are truly magnificent. With that out of the way, let's head on to the first section of this tutorial. All right, so the first thing we're going to look at is atomic prompts. This is the basic of context engineering, just plain prompt engineering. And at the end of this section, we're also going to look at what DSPy is and how it works. All right, here we have initialized the OpenAI client. You need to have your OpenAI API key configured already in the environment files. I have already done that previously, so I can just call client equal to openai.client, and I'll be able to use it to actually call OpenAI with any of their flagship foundation models. Here, I'm just asking a simple question: what is the capital of India? And you'll notice here that we are just passing in that prompt, which is in this case, capital of India, into the openai.chat.completions.create API, where we also pass in the name of the model. In this case, we're using GPT 4.1. And if we run this, we will basically be calling the OpenAI API, and it's going to give us a response. The capital of India is New Delhi. That is correct. Obviously, if I asked anything else like what is machine learning, if I run that, it's going to ask OpenAI GPT 4.1 what is machine learning and fetch us the results. That's the most basic building block. You have a prompt, you pass it to OpenAI or any of the foundation model API providers, and you get back a response, you print it out. Now let's try to ask it to write a joke for us. Well, if we did that, it is writing a joke. Why did the AI get dumped by its girlfriend? Because every time she asks, "Are you listening to me?" it replied, "I don't have sufficient context to answer." I mean, it is not funny. It is something. It tried something. That's all right. Let's see how we can improve these jokes. Let's add a constraint. Basically, right now, instead of just asking it to write a joke about AI, we're also going to give a constraint that says that has to do with them turning rogue. So this is called prompt with a constraint. Basically, we are making the LLM's response space a little more constrained, a little more streamlined into what we really want to see as an output. So if we run this command, and now you'll see that its joke is at least related to AI turning rogue because it couldn't compute with society's bite-sized expectations. Okay, I mean, it's not a funny joke, but at least it did what we asked it to do. So I'm gonna let that pass. Now let's see if we could provide more context. Here we have a constraint as well as additional context. Like for example, here I'm saying a joke contains of 3 sections: a setup, a contradiction, and a punchline. Now, I don't actually know if this is how jokes are written, but I'm just gonna, go with it. And I've also asked it to maintain a jovial tone. Let's run it. And now you can see that it's outputting a setup, a contradiction, and a punchline, just how we asked it to. So now obviously if we run this a couple of times, we're going to see different responses, because remember, when OpenAI or any LLM provider generates response, they use this temperature variable to randomly sample tokens as they are generating responses. So every time you run it with a high enough temperature, you are going to get diverse jokes. Next, let's have a look at few short examples. This is another prompting method where you explicitly tell the AI or the LLM some examples of how you want your responses to be. So in this case, instead of writing that context as I had done previously, which tells that there are 3 sections, I have instead provided examples: setup, punchline, contradiction. I've also added this new thing called full comedian delivery, which basically includes the setup, punchline, contradiction, and then writes a joke about it in the comedian's voice. So let's see if we run this, then what happens. Well, it took a little longer, 2.65 seconds, because I think it has to process the input, which is slightly longer than before. And also the output is also longer because now you also are asking it to generate the full comedian delivery. Now you can see here that you have the setup, punchline, contradiction, and you also have the full comedian delivery. Now, I'm not going to go and read through all of these jokes, but if you want to have a look at these jokes, pause the screen and read it. If you find anything that's super funny, let me know in the comments. All right, so another thing you can do with LLM prompting is assigning it a role. Here, you explicitly tell the LLM what its role is. Now, traditionally, this assigning role thing happens inside the system prompt. But for this example, I'm just using the user prompt itself. I'm going to show how exactly this system prompt thing works here in a bit, but the idea is the same. You basically tell the LLM something about how it is supposed to behave, sort of give it a persona, you give it a role. Here, I'm just giving it the role of a comedian who likes to tell stories before delivering a punchline. And it's always funny. Let's ask it to be funny. And if you run that again, it's another joke. And now you can see that it is generating a story. So the other day I walked into my kitchen, all of that. Next, let's talk a little bit about system prompts. Now, in general, you almost always want to add a system prompt into your LLM's chat request whenever you're using it. Adding it is pretty simple. Now, previously we were just using this user prompt. We are not using the system prompt. Now we introduce this role system content system prompt into the messages that gets passed into the LLM. Let's have a look at how it all works. Now here in the system prompt, I'm first assigning it a role. You're a comedian, you tell jokes, you're always funny. In the next section, I'm giving it some basic context, like jokes contains of these 3 sections, and then it contains this full comedian joke delivery. And I'm passing any additional instructions that it needs, like always maintain a jovial tone. Now you can also input few short prompting ideas into here, like examples of jokes that we saw before. And you can also input things like the structure in which you want your LLM to output. We're going to have a look at that second thing where we ask it to output things in a specific format in just a little bit. But for now, we have this basic system prompt which does not have any information about the content of the joke or what do you want the joke to be about, because that goes into the user prompt. And if you run that, here you see that it also does the same. Setup, punchline, contradiction, delivery. All right, so we have gone some ways into what basic prompt engineering is. You have seen all of this before, so I'm just going to browse through this section and go to the interesting DSPy part, which is coming up in a little bit. Before that, let's just talk about structured outputs. Structured outputs is when you don't want static text like this. Instead, you want it in a specific format which you can use to actually manipulate the data and use different things for different things. For example, here, if I just want the setup portion of this response, I will have to do some regex. I'll have to do some string manipulation to extract these out. Or if I just want the comedian joke delivery, also have to do that. It is very tedious to do all of this. So a simple way which you can get done very easily is just ask it to output in a JSON format. And you give them the format like setup, punchline, contradiction, delivery. And if you run this, you will basically see it has outputted things as a JSON string, and I can do a JSON.loads here and just extract the delivery or the punchline very easily just from that. That is incredibly powerful to use JSON or other structured formats to just extract things from LLMs like that, but they don't always work because sometimes the LLMs might miss a key. The LLMs might output in a format that is not adequate. This can get even more complex if you try to use nested JSON objects, like if you want it to output JSON objects within JSON objects or list of JSONs. So there are all of these cases where the LLMs cannot output things in one shot in the right format. And often you want to check if these formats are correct. And then if it's not correct, you pass it back to the LLM and ask it to correct it. And if you don't do that step, I don't know how you can sleep after deploying an LLM app, because what if the LLM just decide to not output things correctly? Your app is going to crash if it depends on specific keys being present when the thing runs. This is one of the main reasons I decided to use DSPy for this tutorial. Let's see how we can do the same thing that we did there with DSPy. Now, if you ran that, you're going to see that DSPy also outputs setup, punchline, contradiction, delivery, just as we wanted. And if I did something like joke.contradiction, I'll have the contradiction part of it, joke.delivery, I'll have the delivery part of it. It just works. And how you do it is by using this DSPy.signature thing. And the signature contains of 3 sections. First, it contains this doc string. This doc string is basically like your system prompt. It helps DSPy to tell the LLM what this signature is about. Here I'm saying you're a comedian who likes to tell stories before delivering a punchline. You're always funny. Next, it contains input fields. Input fields are things that you must input to this signature. Like in this case, I'm going to input a query like give me a joke about AI turning rogue. And finally, it contains output fields, which contains everything that you need the LLM to output. The cool part is that you can configure this. Like for example, let's say I also want to add something more like speaking style. And you can also add descriptions to these fields. It basically fills up the LLM's context with more information about how you want your output to be generated. If you run that, right now it's giving an error that it's missing a speaking style. So if I also added this speaking style here, and let's say I want you to speak like a math professor, why not? If I do that, now you can see it talks about things like calculate pi to a million digits. Okay, that's how math professors speak. And you may have also noticed this DSPy.predict thing. Well, this is what is called a DSPy module. Imagine your program to be a graph where each node is a text processing unit. You input the things that you need to process this graph, and every node combines different parts of this text information, processes the text, and passes on to the next step. Modules do just that. DSPy.predict is the most basic module where it just inputs all of your input fields, creates a prompt, calls an LLM, and then sends you the output. It is the most basic DSPy module. And as this video goes along, I'm going to show a lot more complicated modules, both from DSPy, and also we're going to create some of our own modules to do our own tasks. Also, to see what is happening under the hood, we can use this inspect history function. Let's pass inspect history equal to 4 and see what is going on. So here's what happened when we ran this DSPy.predict command. First, DSPy under the hood created this system message. Your input fields are query, speaking style, and your output fields are setup, punchline, contradiction, delivery. So you can see that everything that we had used up here is actually being used right there. Then it creates this structure. All interactions will be structured in the following way with the appropriate values filled in, and it contains the structure which DSPy provides to the LLM in form of the system prompt about how this conversation is going to go. Lastly, it also contains this additional objective. In adhering to this structure, your objective is you are a comedian who likes to tell stories before delivering a punchline. You're always funny. If you remember where it came from, this is basically the doc string of our DSPy.signature. So if you scroll down a little bit, that was the whole system message. And now we get into the user message. In the user message, we have the query, which is write a joke about AI that has to do with them turning rogue. And the speaking style is math professor. You'll remember that those are indeed the two things that we had passed in when we called the DSPy predict module. Finally, here is the response. This is the stuff that the LLM had responded. You can see that it contains the setup, the punchline, the contradiction, the delivery. And after this is generated, DSPy does some processing to extract these sections out and create this Pydantic base model object. And the cool thing is that DSPy modules come in all shapes and sizes. For example, you got this DSPy.chain of thought, which is another type of prompting strategy. In chain of thought, we ask the LLM to generate some reasoning text before outputting the final response. Let's also add the speaking style. Let's now use something else like 80s movie villain. Now you have some stuff in a deep, sinister voice. All 80s villains have to have that. And if we had a look at inspect history, let's have a look at that. You can see that now you have everything that previously was there, but here DSPy has additionally included this output field for reasoning. So naturally, when the LLM is about to output things, we also ask it to generate the reasoning followed by setup, punchline, etc. And indeed, that's what happens. The LLM first outputs reasoning and then all of the rest. So that's your basic introduction to DSPy. And as this tutorial goes along, you're gonna look at more stuff that you can do with DSPy and how it really helps with context engineering. If you want an in-depth overview of DSPy, I'll also suggest you to look at this video, which is purely about DSPy and different functions. Some of the materials in this video is a little bit outdated because there have been some API changes, but 90% of that video is still worth watching if you're interested in DSPy. But for now, let's move on to the next section of the video and talk more about context engineering. We talked about atomic prompts, we talked about structured outputs, and we talked about DSPy, but how do we use all of this to do better context engineering? Let's just follow along with this joke example and let's see how much we can extend or stretch this joke to enrich the context even more. In the next section, let's look at multi-step interactions and multi-agent applications. Let's go. Things we have looked on so far has a single chain. We have an input, we process it, we generate an output. Multi-step interaction adds more of these nodes and connects it in a graph. Let's see an example. Here we have the same program that we saw in that notebook. You have a joke signature that contains this doc string. It contains the setup, punchline, delivery, contradiction, all of that as output fields. And then you call DSPy.predict and then write a joke. If we just run this once, sequential flow.py, if you run this, you're basically going to get a prediction object which contains the setup, punchline, contradiction, delivery. Cool. Also, you may have noticed this ML flow thing. You don't have to worry about it right now. This is something we're going to have a look at when we discuss evaluation. So don't let that bother you. Now, what if we want two separate LLMs? The first LLM just generates the setup, the punchline, and the contradiction, and the second LLM generates a delivery. So the first LLM is just concerned about getting a good plan for a joke, like an idea of a joke. And the second LLM is going to then take that idea, process it, and then make a delivery. So our graph is going to look like this. Our first block is this idea generator, which inputs the query, outputs an idea. The idea contains the setup, punchline, and the contradiction. And we get the second LLM, which inputs this joke idea and generates a proper joke. Let's see how we can do that in DSPy. Well, it's surprisingly simple. We input all of the DSPy stuff, then we create this pydantic base model that contains the schema for a joke. It contains the setup, the contradiction, the punchline, as we have discussed previously. Then we write our first signature, which is the query to idea, which is that first block, which is going to input a query of type string and is going to output a joke idea of type joke idea, which again contains this thing, setup, contradiction, punchline. And this is another cool thing about DSPy, where you can do this type of nested objects, where you can declare these signatures with nested pydantic base model objects. And because DSPy does all of this heavy lifting with validation under the hood, it's very easy to just kind of trust it. Now, sometimes it might fail still because the LLM is not very strong. So if you're getting a lot of those types of errors, you can either make your input signatures a lot simpler, or you can increase the size of the LLM and use more advanced models in that case. All right, so back to the code. We have the query to idea thing, which inputs the query, outputs the joke idea. And then you got the idea to joke signature, which inputs the joke idea and it outputs the joke as a string. So we have basically configured the schemas, the contracts, if you say, of what the input should be, what the output should be. We have declared that from the get-go. Now we have to put it all together. Now we have to create that computation graph, how the data flows through it. And that's where we're going to use DSPy.module. Here I've created a simple DSPy.module object. Actually, this n attempts thing is not needed. It's for the next example. We create these two DSPy.predict object, which performs one node transformation. The first one transforms from the query to idea, and the second one converts from idea to joke. And then you got the forward function. Now the forward function is what you're going to use to define our forward pass through this computation graph. It's kind of like PyTorch if you've used PyTorch before. You declare exactly how the data is going to flow through your neural network's forward pass. Instead of a neural network, we have an DSPy module instead, but the ideas remain the same. First, we generate a joke by passing the input query into the query to idea predict function, which, remember, is just this signature, which inputs a query, outputs a joke idea, and then finally, you pass in the joke that you received here back into the second DSPy module to convert it from an idea to an actual joke. And to run this module, all you need is to create the joke generator object and then run it by passing it a query. So here I'm just again using the same prompt, write a joke about AI that has to do with them turning rogue. Now if I run this now, let's see uv run t1 sequence.py. If you run that, now you can see that first, it generates this joke idea, which contains this prediction object that contains the setup, the contradiction, and the punchline. And the second LLM then outputs the joke itself by converting this joke idea into an actual joke. Isn't that amazing? You've created the most basic form of a multi-interaction LLM system. Now, again, I must remind you, this example I'm using of writing jokes and all this is just an example. You can use the same concept into any LLM application that you're building. And in the next section, let's look at another idea, another type of multi-interaction system where an LLM, given a response, then iteratively improves upon it to generate better responses. This process is called iterative refinement. Basically, once the LLM's response is generated, we pass it back to the LLM sort of to reflect on it. We ask the LLM to think if there's any scope of improvement, and if it thinks that it needs to improve, output a refined version. Let's see how to apply that with DSPy. Well, first we have our usual stuff, then we create the joke idea. Up till here everything is the same. Let's apply this refinement idea into the idea to joke signature. Our goal is, after we generate the first joke idea, we are going to create one joke draft and then iteratively improve this joke. Let's see how this signature looks like. Here we have the joke idea, which is an input field as we previously had, and we have the joke itself, which is something we're going to want the LLM to output. So that's an output field. The two things we have are draft joke and feedback. Now, you'll also notice I have used the optional keyword, which I've imported from typing. From typing, import optional. Remember, these things get processed into Pydantic base model objects in the end. So if you're familiar with how Pydantic base model objects work, you can use any type annotation that you want. You can also pass any description or any keyword arguments that you want that you would normally pass into a Pydantic base model object. So for example, if you want to generate an integer between 1 to 7, let's say rating int, you can basically say dspy.output field and then use things like gt equal to 1, le equal to 7, and this would also work because you're setting up the Pydantic base model to validate that your response is between GT1 and LE7. Anyway, coming back to our draft joke and feedback, we have annotated them with optional, meaning we may or may not pass it. Finally, we also have this refinement signature. This is new. Here we are passing in the joke idea, which we got from the first LM. We also pass in the joke, which we got from the second LM, and we ask the language model to give a feedback or to give a change. We can also just call this a feedback. Maybe that's more appropriate. Inside the iterative joke generator, we now also pass in this n attempts thing. We're going to use this n attempts thing to configure how many times the refinement module runs to try and improve upon the language model's joke. We create our DSPy modules next, and let's look at what happens inside the forward function. Well, first we do the query to idea thing as we were doing before. Next, we loop over this block of code n attempts time. First, we generate a joke from the idea. You notice that we pass in the joke idea, we pass in the draft joke, which starts off as none. We pass in the feedback as well, which also starts as none. And then we call this self.refinement module, which inputs the joke idea and the joke itself that got generated by the idea to joke module. And we are pretty much done. It basically loops around n attempts time and it generates a joke, generates a feedback, and in the next step we pass in the last generated joke and the last generated feedback into the module. And finally, after all that is done, we generate the final joke and we pass that back to the calling function. Let's see how it looks like once we run it. Let's have a look. So at the first, we have generated the joke idea. Again, you can feel free to pause and read some of these jokes, and if you like any, please do comment and let me know if there's a gem hidden here. Iteration 1, the first time it ran, it generated a joke, then it generated a feedback. Notice that we are using the chain of thought module here. That's why it also has generated a reasoning string, and followed by that you get a feedback. It says the joke is pretty good, whatever. It does generate some additional feedback, it seems, and then we rerun the module to generate another joke prediction, another feedback, and finally, after 3 iterations of this, we finally get our last joke. That's how iterative refinement works, and you can use iterative refinement in every module you wish to. The drawback of using iterative refinement is that it increases the latency of your applications. It increases the token cost of your applications as well, and so it makes things more costly. A little bit later on the video, I'm going to talk a little bit about evaluating all of these algorithms. Like, how do you know what is a good idea for this n attempts variable? Like, is it 3, is it 2? Like, how do you judge what might be a good value that balances the trade-off between a really good joke generation and something that's latent enough for it to be useful as well as cost effective? But before that, we're going to talk about the next algorithm, conditional branching. The goal with conditional branching is pretty simple. Depending on a response, you get to decide 2 control flows. For example, if a particular condition is met, execute graph A. If it's not met, execute graph B. That in itself opens up a lot of possibilities. So let's have a look at how exactly we're gonna do that. All right, so in the last example, we added a module to the joke generation to iteratively refine it. Let's now add a module to the joke idea generator. What if after a joke is generated, we assign it a rating? And if that rating is high, we proceed to generate the joke. And if it's not high, we ask it to generate a joke once again. Let's see how to build a simple conditional branch like that. Well, we start as usual. We have our joke to idea. We have our query to idea. It's all the same till now. We also have the idea to joke. Notice I have removed the draft joke and the iterative refinement part to keep this example contained and simple, a little bit easier to follow along. And the new thing here is this joke judge. And what the joke judge does is pretty simple. It's visible from the code, and that's the beauty of DSPy. You just say what this signature does. Is this joke idea funny? What the joke idea is, which is an input field, and what is a joke rating, which is an integer between 1 and 5. Pretty simple stuff, right? Let's see how we are writing the DSPy module though. Well, first of all, we define this thing called max attempt. This is how many times I want to keep trying to generate a good joke idea. Let's also add another variable here. Let's say good idea threshold, and let's set that to maybe 4. And let's say self.good idea equal to good idea threshold. All right, everything is simple here. You have a bunch of DSPy modules. Let's look at what happens in the forward function. Here, first we have this for loop, which is going to do this judge stuff. And after all of it's done, we are just going to call this idea to joke. Again, remember the graph. Always remember the graph, because whatever you design in that scratchpad is what you're eventually going to end up writing here in code. So hopefully the flow makes sense. Now let's look at what the flow actually is. First, you generate a joke idea, and then you generate a judge score. The judge score inputs the joke idea, passes to the self.judge thing, which again is a chain of thought which operates over this signature. Inputs the joke idea, outputs the joke rating. And once you find out what the judge score is, you are going to basically pass that in here. So self.good idea threshold, if it reaches the threshold, if it's above that, the judge said it was awesome, skipping it. So once the judge decides the joke is good enough, you break the loop, you go out of the conditional branch, and now you have an idea to generate. Let's look at how this code runs. And you're going to soon see a fundamental problem with LLMs. UV run conditional branch. All right, let's see. So the first idea it generated, the judge said it was awesome, 4, and then it generated an output. See, LLMs have a positive bias. You provided something and then ask it, hey, is it good? There's a good chance that it's going to say, yes, it's good. That's why if I run it a lot of times, it's not going to rate it any higher or rate it any lower. It's just going to say it's good and move on. What we instead need is a comparative option where we pass the LLM with multiple joke ideas and ask it to figure out which one is the best and then move on with the one that it picked was the best. For that, let's move on to the next section of this tutorial where we're going to talk about multi-output systems. All right, so what is our new graph? Well, we again start with a query, but this time instead of running the joke idea just once, we run it multiple times, let's say 3 times. So we generate 3 different joke ideas. These 3 we pass into the judge, and the judge's role is to rank each of these. We are forcing the judge to pick a side, which one is good, which one is bad. And the one that it picks as the highest, we pass it on to the next LLM to actually convert it from an idea to a joke. Let's see how that looks like. So you have the joke idea as usual, you have the query to idea, which is also the same as it was before. You also have the idea to joke, same as before, except here instead of ratings, we wanted to output the rankings. Rank 1 is the most unique and funniest. Let's see how the module looks like now. We define all of our modules up here in the constructor, and then you see this async def a forward. Now async programming basically means you're parallelly processing different input output requests. You see, if you remember our graph, we don't need to wait for previous joke ideas to finish to generate the next idea. We kind of want all of it in parallel, and for such use cases it's best to use async programming. And with DSPy, to do that, instead of overloading the forward function, you have to overload the a forward function. Also, the cool thing is that every DSPy module already implements the a forward function natively. So to call a function and have it execute asynchronously, you use this a call function instead of just calling it as we had been doing before. So here we are generating num samples, number of ideas directly using the a call function, and this async io.gather basically runs them in parallel, so you're effectively generating them parallelly. And once they are generated, we already have the ideas. We pass that into our judge. Notice the joke judge actually inputs a list of joke ideas instead of a single joke idea as it previously used to. So we've also made that change. And once we have generated them, we are going to find the index that the judge had scored as rank 1, meaning that's the best joke. And we're going to move forward with that joke and pass it into our idea to joke generation. Now, before I run that, I must also tell you that this step right here is not guaranteed, right? Like the LLM can just decide to not output 1 for any of the jokes. And for that, we use something called as DSPy.refine, which is our next example. But you don't need to have to worry about it right now. I just mentioned it so that you're aware that just because we have politely asked it to generate rank from 1 to n, it is not guaranteed that it will do that. So we can do additional guardrailing to confirm or almost confirm that it always works. All right, let's run this code and see what this looks like. All right, so I can already see that 5 joke ideas have generated like that, because again, we're using the async IO library to generate things parallelly. So you got this 5 jokes. Then the judge has actually ranked these 5 jokes. It ranked the first joke at number 3 position and the fourth joke at number 1 position. So this one. And so our selected index is index 3, which, because it's a 0 index thing, is 0, 1, 2, 3, which is rank 1, which is this one. So the selected joke is this. That is the one that got passed into that next module, where it basically generated the joke as we had intended to. So you've already learned a lot. You know how to generate multi-step sequence, which are just flat out no branches. You know how to generate loops by using that iterative refinement option. You know how to generate branches because we did some conditional branching. You also now know how to generate multiple things in parallel and then take decisions off of it. Now, the next thing I'm going to show you is refinement. Like, how do you confirm, for example, here that the LLM does indeed generate things correctly? Let's see how that works. Frankly, it's pretty simple. Instead of defining the judge as a DSPy.chainOfThought object, we instead define as a DSPy.refine object, which inputs the DSPy chain of thought joke judge and also a reward function. We define a reward function very simply. Here we are checking if all the ranks are present between 1 to 5. And if that happens, we go through with the same formula as before. There's no change at all in the forward function itself. We parallelly generate queries and then we generate the judge scores. Let's run this and see what happens. Again, we have our joke ideas. We generate the scores for each of the ideas. And finally, we generate a prediction. Now, a cool thing here is that this was already working, right? So I'm not really demonstrating the power of refinement. Let's change the all rank present slightly differently. Let's remove this +1. So now, instead of asking the LLM to output the ranks between 1 to n, we basically want the LLM to output ranks between 0 to n-1. Obviously, the LLM does not know that right now because we have not told it in the description. But can DSPy.refine tell that to the LLM? Let's see. Let's run the code again. And here you see it has indeed picked 0, 1, 2 instead of 1, 2, 3. Now, what has actually happened under the hood? Well, the best way to find out is actually to have a look at MLflow, which I'm going to have a talk about a little bit later on in the video when I discuss evaluation. But for now, let's just add a breakpoint here and look at what really happened under the hood using the inspect history function as we did previously. All right, so we are into the breakpoint. Let's have a look at self.judge.inspect history. Let's say n equal to 4 once again. And here is the history of things that have happened in the module. So if you scroll all the way up, it starts with a simple system message. Here, the only information the LLM receives is rank each joke score idea between 1 to n, which is something we had specified in the doc string of the signature. So nothing yet has happened which has anything to do with that reward function we wrote. All right, so we pass in the user message as usual, and then the LLM response. All 3 jokes are good, and they generate some ratings, 1 to 3. Cool. Now what happens is that DSPy.refine checks the rewards and sees if the reward is greater than this reward threshold that we had specified here. We had specified the threshold of 1, but obviously the reward it got is 0 because we want things to be 0, 1, 2, not 1, 2, 3. So then it generates a new system message where it's giving the program code, the module's definition, and all of this. And what's really happening here is that we are passing the reward code as well. So we are effectively filling up the context by informing the model everything it needs to know to update, to provide feedback to the original language model about how you can improve on this reward. And so the response of all that is that the module produced joke ratings that did not include all ranks between 0 to n minus 1, instead producing ranks starting at 1, including out of range values like 3. And that is what refine does. It takes everything that you had generated, it takes your reward function, it takes the last generated LLM output, and it generates an advice. And this advice is, if you scroll down a little bit more, this advice is basically sent in as a hint back to our judge. And now, after looking at the hint, it is finally able to output the ratings in the correct format. So hopefully that sort of informs you how powerful this DSPy.refine thing can really be. You can write any reward function, and as long as it's self-contained, like all of the logic is present inside this reward function, you can basically use it to guide your LLM's output according to whatever you need. Pretty handy, but as you can also notice, it does consume a lot of tokens. It does run for a long time as well. So there's a latency factor, there's a cost factor to it. And that's why use it sparingly and use it when you really need it. Another cool thing which I have not talked about yet is you don't need to use the same language model and the same temperature setting for each module of yours. For example, let's say you want the joke module to use a larger language model like GPT 4.1 instead of GPT 4.1 mini, or Gemini 2.5 Pro or Gemini 2.0 Pro instead of Flash. To do that, you just need to do this one line. You just mention the name of your module, which in our case is this chain of thought idea to joke, and you write set lm dspy.lm, the name of the model, and any temperature you want. And if you did that, you can manually set which module should use which LLM to generate its responses. That is insanely powerful, and that gives you low-level control of everything you need. All right, so we're almost done with this section 2. The final example, the final thing that I want to show you is the idea of reflection, which is kind of almost similar to iterative refinement. But in iterative refinement, you had two modules that refined one idea. And in reflection, you basically use the same module to internally reflect on its previous responses. The idea is pretty same, but I think it's handy to know both methods. So I'm going to quickly show you the reflection approach. Again, you have the joke idea, you have the query to idea, idea to joke, everything there. But now you can see in idea to joke, it's slightly changed. First, you have the previous doc string, but now you have additional instruction that I've added that if you're provided a draft of a joke, meaning something you've generated previously, your goal is to make it funnier and more punchy. And then you also have the joke draft, which is an optional string, which is an input field as well, that is used to declare any existing joke that you may have already generated. And finally, to do this iterative reflection, you basically run a for loop and you pass in the joke idea and you pass in the joke draft, which is basically the previously generated joke, which starts at none and then get updated as this loop runs. And if you run that, we run t4 reflection.py. First, you generated a joke idea as you were doing previously, and then iteration 0 is one joke, then iteration 1 is a different joke, and there's some reasoning behind the changes, and iteration 2 is another joke. So with every iteration, you're processing the text further, asking the LLM to make minor corrections to make the joke funnier and more punchier. All right, so we have seen some approaches of how to create these graphs. You create a graph on your head, you think about things that would help the LLM, and then you generate a graph out of it. And then from the graph, you write code. You first generate the signature that defines your inputs and outputs, and then you write the module which defines how the forward pass is going to happen, how these nodes interact with each other to process your text. As you can see, it is easy to just write some of these graphs and generate some of these jokes. What's harder is to evaluate what's good, what's bad. And what's even harder is to find hyperparameters that maximizes the performance. So in the next section, let's have a closer look at how you can evaluate things using MLflow and various other tools. All right, I recorded a bunch of that yesterday. and it was getting dark yesterday. So I decided to come back today, the next day, and record this next section. We're going to start with evaluation today. So for some reason, people don't want to talk about evaluation. I know it's kind of the more boring aspects of any software development. You just want to go, build features and all this. But evaluation is very important, and it is the make or break for most LLM apps. So I'm going to give you some pointers, some ideas about how to evaluate these systems and take the best decisions from a data-driven point of view. All right, so there's a couple of different aspects that you need to think about when you think about evaluation. First, you can think about it as observability, like what is the LLMs inputting, what are the context filled up with, and what are the LLMs outputting. This also might contain things like monitoring the LLM's cost usage, like the number of tokens it's using, the latency of different function calls, and everything like that. The second aspect of it is evaluating with metrics. Now, this is very important. When you start making LLM applications, it is important that you plan ahead of time how you're going to evaluate it. It not only helps you to scope out your application, it also helps you to think about what the best case scenarios are. The third thing that you need to think about is optimizations. Like, is there a way that you can use existing evaluation metrics from step 2 to optimize your prompts or optimize different parts of your algorithm or functions to make things better? In this video, I'm just going to cover step 1 and step 2. For step 3, I'll once again ask you to watch my old DSPy video, which contains some additional information about fine tuning, and have a look at some of the DSPy optimizers from the official DSPy documentation page. So the first thing, observability. Let's look at how you can do some basic observability, and we're going to use MLflow for this. If you're not familiar with MLflow, it's a classic platform to track your machine learning models, track different experiments, and these days people are also using MLflow for tracking usage and tracing functions for LLMs. Let's see how tracing works with DSPy. You can run MLflow on a remote server where all of your experimentation data is going to be stored and you can view them through a dashboard. But for our case, we're just going to run it locally. And the command to do that is pretty simple. It's just this. It's going to use SQLite to store all of the data. And we are starting the server at port 5000. If I go to that URL on my browser, I can see that MLflow is running. Now let's see how to actually do experiments and track them. Funnily, everything you need to actually use MLflow with DSPy are just these few lines. The first line is just, well, importing MLflow. The next line just turns on the auto logging feature. So any OpenAI call, any DSPy calls are now going to get tracked by MLflow. The third thing is just we tell it where the MLflow server is running. So for our case, it's in localhost 5000. And finally, we set a name for the experiment. So everything we do, every time we run this code, is going to save the information inside this reflection experiment. That's it. I can just run the code now. Let's try to run it. UV run t4 reflection.py. Let's run it and see what happens if we run it. So the first thing you see is that it created an experiment named reflection because it does not exist. And then the code runs as usual. There's nothing new here. But if I go to this page, reflection and traces, you'll see that there are some records. Now, some of these are 5 seconds, 4.6, and there's one that's really high, like 17 seconds. The thing is, this 17-second one is the entire function that ran. So the input to that function was the query, and the output was the reasoning and the final joke, which is basically this entire function. Because remember, this function, this conditional joke generator, is also a DSPy.module. So every time you add MLflow trace to a DSPy module, it's going to track its input and output. And not just that, it also tracks the intermediate steps. Like, for example, you have the predict.forward, which inputs a query and outputs this joke idea. And if you look closer, this predict.forward thing runs twice because, again, we have set the number of samples to 2. So it has generated 2 joke ideas and both of them have been captured right here. Then you have the refine.forward, which, if you remember, after we run the joke ideas, we basically call the judge thing, which is a DSPy.refine module where we pass in those joke ideas. So if you clicked on refine.forward, we will see that it indeed contains two joke ideas, this first one and this second one. And the output for this are the ratings. Another really cool thing about all of this is that we are also tracking the individual modules outputs as well as separate traces. So for example, here you have a light LLM completion call where you can even see the completion tokens and all of the usage details related to a specific LLM call. It's just insane. It is super useful to have all of this at your disposal. And again, remember, we just needed to write these 4 lines and start that MLflow server. So there's no reason to not do it when you're developing locally. If something failed in between, like let's say we tried to return some sort of error, raise exception, something went wrong, and then let's save that and run it. Well, now you see that there was an exception, and if you refreshed it, you'll also see that an error message has popped up. So anytime there's errors and all that, you can also find logs of that very easily. There are also other alternatives like Lockfire, Langfuse, but for DSPy, I've been using MLflow and it's been pretty good. All right, so the next thing we're going to talk about is the concept of evaluating your responses. Now, evaluation is kind of tricky because it really depends on your project and it depends on what the use case is and what your outcome expectations are. So for every project, there is probably a different ideal evaluation strategy. But one thing is common among all of them. You need to plan it ahead of time. Like before you start writing code or ideating, you need to figure out how you're going to evaluate it. Now, you can do it in a couple of ways. You can write unit tests for each module. And the second option is to do an end-to-end testing where you input a query, you output something, and you evaluate how good the final response is. For projects where you already have a data set where you can compare very easily, like if the answer was correct or not, you can change some of the hyperparameters, generate responses with each of them, and then see which hyperparameters lead to the best accuracy versus latency trade-off. For some projects, it's hard to generate a data set beforehand, but you can generate simple reward functions like objective functions, which you can pass your LLM's output to and get a numeric score about how good it is. If you can design your project to have this kind of a reward function for either specific modules of the project or the whole end-to-end thing in general, then you should build it like that because it makes the task of evaluation very easy. The third kind of project is where the responses are kind of open-ended. You cannot really write a simple objective function in Python, or you don't have an existing data set to match your answers with. And that's where evaluation is a little more trickier. And I've purposefully picked one such project. We are working on this joke generation system, but it is not easy to verify if the jokes are funny. Like, I'm not going to go and read through each of them. So a common way to use evaluation in systems like this is to also use another AI model, maybe a larger AI model, to judge if the joke is funny or not, or to judge your open response is good or not. So a simple way to get started with open-ended systems like this is to just generate a bunch of data with different hyperparameters. For example, here I have a simple script that generates a bunch of different hyperparameters that I want to test. I've declared those hyperparameters here. I've declared the number of trials or the number of different samples and combinations of hyperparameters I want to use to generate responses. I've just picked 10 here, but you can pick a lot higher to get better results, I guess. And finally, I'm going to loop over num trials time, or 10 times. I'm going to randomly select one thing from each of these lists, and I'm going to run my conditional joke generation algorithm with those set of hyperparameters. All right, so after we said that, we generate some jokes, and we are just going to save everything in a data frame and save it locally. You can also track things like the usage, like the number of completion tokens, and you can also track the latency, like how long it took to run it. So after we generate all this data, we will finally have a simple CSV file. I'm just going to show how that CSV file looks like. We have the joke language model, we have the idea language model, we have the final joke that was generated from all of that, and we got the latency as well. So after we have this data set, we can now compare between them, assign ratings to each of these jokes individually. Because remember, LLMs have a positive bias. We want to make it a scenario where the LLMs has to choose between 2 or more jokes and then pick one, and then we're going to assign scores to that. So to do something like that, one way is to do ELO scores. Basically, we're going to pick two random rows from this CSV file and then ask a judge LLM to tell us which one is funny. We can also increase the temperature and ask the LLM multiple times, or ask multiple different LLMs multiple times, and get an average of which joke was assigned a higher score a higher number of times. By repeating this a bunch of times and randomly picking two different jokes and assigning a score of who is better, we would have effectively created an ELO dataset, like which of the jokes are generally funny. If I just quickly show how that ELO function thing looks like, I have just defined this joke comparer DSPy signature, which inputs two jokes and outputs a verdict. The verdict is an integer between 1 and 0. So if the LLM outputs 1, it means this joke is the winner, and if the LLM outputs 2, it means this joke is the winner. And to do the ELO test, it's pretty simple as well. We define the number of contests that we want to simulate. For example, I'm just picking 25. So we're just going to do 25 comparisons randomly. Then we pick two random indices from our data. We pick the two jokes from those indices, and then we parallelly call our comparisons function to generate the comparison output, and we save it inside this CSV file. I'll quickly show what that CSV file looks like as well. So here we have the same data that we had before, but now we also have these two additional columns, the picked and the won. The picked says how many times that joke entered into a contest and the number of times the joke won. Now, after you have all of these data available, now you can do any type of data sciencey things. You can basically write a simple notebook like I have it over here, which just goes over this data and finds information that you might find useful. Like, for example, drawing some kind of a latency thing, like drawing out how many times IDEA LMs win. Apparently, when we use Flash, we win a lot more than when we use GPT 4.1 mini. The latency of GPT 4.1 mini is slightly lower than Gemini Flash. So comparing just these three things, it makes you feel that Gemini 2.0 Flash is probably the better model for this choice. Again, I'm not passing a verdict on any of these models. I'm just giving an example here. This might drastically differ with a larger data set with different jokes and depending on the applications, honestly. So you should do your own research. I'm just kind of laying a groundwork here about things you can do. I'm not showing any particular bias towards any model. Another interesting thing is plotting things by temperature. It seems that when we use a temperature of 0.7, it has a high win ratio as well as a low latency, which is interesting. Apparently, when we set the temperature to 1.2, the latency goes by quite a factor, actually. That's interesting. Anyway, I hope you understand the point of all of this analysis. The goal for you is to approach this thing as a data scientist. It's not just about making applications that sound smart on paper. Sometimes a simpler solution may actually win. So you have to build a framework where you can test quickly if a change you made is actually leading to better results, better latency, better accuracy, better jokes, anything that your application needs to do. Okay, so that's my TED talk about evaluations. Now, I'm not going to keep coming back to MLflow and all of these graphs anymore after this section. And instead, the rest of this video is going to feature tool calling, RAGs, and a little bit about memory. I'm assuming that I've convinced you that evaluation is important. So assume that all of those modules also need their own evaluation strategies. So when you're designing all of them, keep that in mind. All right, with that out of the way, let's go into the next section and talk about tool calling. All right, what are tools? Well, you can imagine tools as simple Python functions. Python functions that your LLMs can call when they're generating responses. Let's see how that works. For our example, let's just use a simple web search tool call. Basically, our goal is to ask something to the LLM, and the LLM is going to decide if it needs to do a web search. If it decides yes, that it does, it will call our web search tool. Our web search tool is actually going to perform the web search and return us the results of the search. The LLM is then going to read the search results and decide to take another action. To do the web search, I'm using Tavily. You can use X or anything else as well. To do this, we just define a basic Python function, and then we call the Tavily client to do the search. So for example, here I'm searching about the International Math Olympiad, IMO, and you can see that one of the results was about OpenAI completing that significant milestone in AI development where it achieved gold medal performance in IMO. Now, how do you make LLMs use these tools? Well, for that, let's write a simple agent. Let's call it the haiku generator. And in the doc string, we basically say that it generates a haiku about the latest news on the query. The input field is just a query. Then we want it to output a summary and a haiku. And then the module we're going to use is called DSPy.React. React stands for reasoning and acting, and it's a way to use tool calling agent. Basically, the model looks at the input request, then decides whether or not to call a tool to gather more information or generate the final response. Notice that it also contains this max iteration parameter, and the tools is not just one function, but it's a list of functions. So you can pass multiple tools into the React program, and the LLM will have the option to select which tool to call. And the max iteration is the number of tool calls that the LLM can make in total at the max before it must respond to your initial query. So for this, I'm just going to pick a max iteration of 1 because frankly, it just needs to make the recent news tool call just once. So if I just do that, let's see, uv run tool calling agent.py. If you run that, let's see what happens. And here you can see that the summary is OpenAI's latest AI model has received a gold medal performance, which is great. Remember, without the tool call, the LLM would not have access to this information because its training cutoff did not include this recent achievement from OpenAI's models. So tool calls is the way to go to fetch recent information as well. And then it writes a little haiku for us. And then I have printed out the inspect history to see what really happened under the hood. You see the first system message asks the React module to output 3 things: the next thought, the next tool name, and the arguments for the next tool. And if you scroll down even further, it also gives a list of what are the tool calls that the React program has access to. The first one is a fetch recent news, which if you remember here, that's the name of our function. And the second one is this finish one. Basically, when the LLM decides that it has enough information to actually generate an answer, it can pick the finish tool call. Next, if you scroll down even further, there is some additional information like what the actual request is. And this part of the prompt comes from the doc string that we wrote about haiku generator. Then it contains more information about that is specific to the DSPy.React module. And if you scroll even further, you'll see the tools that it has access to and additional details. For example, for the fetch recent news, whose description is inputs a query string, search for news, and returns the top results. And we had actually defined that as a doc string right here. It also says all the arguments that it takes. For example, the query is of type string. Next, you have the finish tool, which is defined by DSPy automatically, whose description is marks the task as complete. That is, it signals that all the information for producing the outputs, that is the summary and haiku that I need, are already available to be extracted. Awesome. So after that, we have the user message where we pass in the query that we had sent in. Said program query equal to OpenAI. So that's the OpenAI query that we had sent in. And then you can see that from all of that, the LLM response, it's thought to write a haiku about the latest news on OpenAI. I first need to gather the most recent news articles related to OpenAI. So the next thought is that, and that's why the next tool name, which is the tool it wants to call, is the fetch recent news tool. And then it also decides what the query should be, and it generates this JSON string with the query being OpenAI. And that's it. That's its first response. So internally, DSPy is going to parse all of that, and then it's going to call the fetch recent news function with the OpenAI query. And you're going to see how this fetch results is passed back into the LLM in the next section. In the next system message, if you scroll down and further and actually go to the user message, you'll see observation 0. And here you have all of the information, like the specific news articles that was fetched. All of these articles, basically, they are coming from that Tavily API. And if you scroll down at the end, now after the LLM consumes all of that information, it now reasons that the recent news about OpenAI highlights 2 major developments. So it understands all of the developments, then it summarizes it, and then it generates the haiku. Recently, people are also using MCP servers. You can imagine MCP servers as an API server that contains different tools with doc strings and additional documentation that helps LLMs to use them as tools. I'll leave a link to a GitHub repo that contains a lot of cool MCP servers in the link below, so be sure to check them out. And to use MCP servers with DSPy, it is pretty simple as well. First, you extract all of the tools that are hosted in an MCP server, and then you just pass it in like this. The amount of things you can do with tools is insane, and LLMs are getting fine-tuned these days to be good at tool calling. For example, if you're using an AI code editor like Cursor, or even things like Claude Code or the Gemini CLI, you'll see they have access to a lot of tools that can directly manipulate files, like read files, do grep searches, write files, and all of that. You can imagine tools as different things that the LLMs can do, like as actions in your environment. For example, here I've just added a simple instruction that also create a simple file where you can save the final summary. And I've also written a simple function that it can use as a tool to write things into a file. We have added the text and the file name itself, and we're going to just write the text into the file name. And finally, we have added it to the list of tools. I've also increased the max iteration to a higher number so that it can get to call other files as well. Okay, finished running, and here you can see that we have a new file, and if I do that, you're going to see that it has also written it into the file. Next, let's go back to our joke generation thing and find a way to incorporate tool calling into the mix. Here, all I've done is in the idea generation pipeline, I've just added the tool. So basically, we had the joke idea and the query to idea, which you remember inputs a query, outputs joke ideas. Now, instead of just outputting any random joke idea, I want to output joke ideas that is related to recent events. And to do that, when we are declaring the query to idea module, instead of using the DSPy.predict module that we had previously been using, we are going to be using DSPy.react instead. And the tool that we're going to use is the fetch recent news tool. All right, let's run that and see what it looks like. uv run main.py. Okay, I'm gonna type OpenAI, that's a query. And the hope is that the joke that is going to come up is going to feature recent events like that International Math Olympiad thing. Let's see if that actually happens. All right, you can immediately see that the joke ideas does mention International Math Olympiad, which again, it's getting that information from that Tavily search that we had set up as a tool call. And the final joke is indeed about International Math Olympiad. OpenAI's AI just won a gold, and then it makes some joke about all that. We're gonna come back to tools when we discuss memory and how you can use tools to manipulate the LLM's memory in just a little bit. But I hope that just this small introduction is going to get your brain running about how you can use tools. All right, so in the next section, we're looking at Retrieval-Augmented Generation, or RAGs. Let's go. I have an entire video that goes into the nitty-gritty and the details about how different modules inside the RAG system work. So please go check that video out for a deeper understanding of the concept. But here I'm just going to stay at a surface level and explain what RAGs really do. The most basic form of RAG is as follows. Given an input question, you want to query a database of relevant passages to find an answer. The database returns you a selection of documents that could be relevant to answering the query. The LLM ingests these documents, looks back at the user's question, and then outputs a final response. This is the most basic form of RAG, and often it works on simple use cases, but for most use cases, you need more complicated stuff. Like, how are you doing the retrieval? Is it a semantic retrieval? Is it a keyword-based retrieval? Is it a hybrid of both? How are you processing the original query? Are you directly querying with the user's query, or are you transforming this query using some sort of a query rewriting strategy to do the search? How are you post-processing the incoming documents? Are you searching over your database just once, or are you doing a multi-hop strategy where you keep searching information a lot of times? All of these questions are important when you're designing a RAG application. Let's build a simple one for our joke use case. I found a dataset called Short Jokes from Hugging Face, and that contains some one-liner jokes. When the user asks to generate a joke, we are also going to query our database of jokes to find relevant material and then pack all of that into the context of the LLM to make it aware that, okay, these are some one-liners that people have found funny in the past. So when you're generating and writing that final joke, maybe you'll use one of these themes to output the answer. I've already downloaded this dataset, by the way. It's just a bunch of these one-liners. And so what I've done is I have embedded each of these sentences. To do this, I've just run the classic DSPy model. So if I quickly show what my data directory looks like, it contains a text file of joke. So if I just do a head of data/joke, it is just a bunch of these jokes. And if I show you what the numpy file looks like, data equal to np.load data slash and this file, it's 50,000 jokes, and for each we have a 768 dimensional embedding vector. So now let's see how basic embedding retrieval really looks like. Let's see basic rag.py. This basic embedding rag class inputs the text and the embeddings, and then to do a nearest neighbor search, it inputs the query and then embeds the query using our DSPy model, and then does a dot product, which is all of these embeddings are already normalized, meaning their magnitude is already 1. A dot product is the same as cosine similarity. Basically, it calculates the angular distance between the two vectors' direction. And finally, we do some arc partition stuff to find the k most similar texts that are relevant to our query. And if we run that, we run basic rag.py. So here I'm just searching plants and trees, and you get some jokes about trees and cats and interesting things. Okay, obviously here I'm saving the entire embedding database in memory, but that is not always possible to do. Sometimes you need vector databases to store all of your embedding vectors, especially if you have more than 100,000 vectors, for example. That's probably the best way to do it. You can also get away with saving things in memory like this for most small applications. So sometimes you might also want to do approximate nearest neighbor search. So for that, a common way to do that locally is to use something called as the annoy index that finds approximate nearest neighbors. So to run the annoy version, we do something called as creating an annoy index, and after we create the annoy index, we just call this get nearest neighbors by vector function to extract the k nearest neighbors. Another way to do search is using something called as the BM25 index. Basically, the embedding approach uses semantic retrieval, meaning it retrieves based on the embedding vectors, and BM25 does keyword-based retrievals. Basically, it checks for specific keywords to have occurred in both the query and your target dataset, and then it ranks them based on the keyword overlap. So for example, if we use the query of cell phones, you'll see that the jokes that it retrieved also contain cell phones, cell phone, cell walls, cell shading. Now, these are not exactly semantically aligned, but often BM25 is exactly what you need for your use case. For example, suppose you're doing some retrieval over refrigerator manuals and you have a specific key that you want to search. If you do a semantic search, it might fetch results from multiple different refrigerator types. But if you do BM25 or other keyword-based techniques like TF-IDF, you will be able to search with specific keywords like the model name of the refrigerator. So are you going to choose semantic retrieval or BM25 or keyword-based retrieval for your RAG projects? Or can you choose both? Turns out, yes, you can. You can use something called as reciprocal RAG fusion. Here's how that works. Basically, to do reciprocal RAG fusion, you input two ranked lists. Maybe one is coming from your semantic search and one is coming from your BM25 search. You can also generate these ranked lists by any other methods, but after you have these lists, what reciprocal RAG fusion is going to do is it is going to rank every item in the list depending on how many times it occurs in different lists and in what positions. So you're effectively combining two different lists, fusing them into one by assigning scores to every item. So if a document appeared on multiple lists, it's going to rank higher. That's how reciprocal rank fusion works. So let's now think about a way to incorporate all of those RAG stuff into our joke generation pipeline. This is our plan. Given the user's original query, we are going to generate a BM25 search optimized query and another query to do vector search. Then we're going to perform this search, retrieve some documents. We're going to repeat this search 3 times to do multi-hop search, and then combine all of that and send it back. Let's see how we can write this pretty complex thing very easily with DSPy. Here the inputs are going to be the query and the previously retrieved jokes. We are going to output the BM25 query and the semantic query. And then we write this multi-hop hide search thing, and that is going to contain a chain of thought module for that hypothetical doc and the embedding retrieval and the BM25 retrieval as we had previously made. And then we're going to call the predict function with the input query and the previously retrieved joke. And then we extract our semantic query and our BM25 query to find those lists. And finally, we do the reciprocal rank fusion. Let's see what happens if we run that. Let's do the n hops to 1 so that we can see what's actually happening under the hood. So you can immediately see that the BM25 query is short because you just want this short queries, and the semantic query that the language model generates is much larger because you want to have a fully expressed out vector, and that generates us a bunch of these jokes. And if we increase n hops to, let's say, 3, it basically updates the queries and all this, and finally we have a bunch of jokes. All right, so finally, now that we have figured out a way to do this kind of agentic search to get back nice results, we want to pass them into our language model to help it to generate good jokes. Let's see how we can do that. So here, back in our joke generation, we have now initialized the multi-hop height search. And here we're first gonna call our idea generation. Then we're gonna make a simple query that contains a query setup and punchline. And then we retrieve some punchlines using our height search. And lastly, we pass the punchlines into the joke generation to generate jokes. And that is basically it. If we run this now, and let's say men, we did some BM25 and semantic searching here, and finally the language model generated this prediction. Now I actually also updated some things about the joke generation part as well. For example, now the joke generator not only inputs the punchlines, but it also outputs the indices of the punchlines that it found useful. So for example, the inspiration it took was gonna make a long joke about gastrointestinal problems, but I digress. I digest. Okay, that's funny. Anyway, so it's going to use all of this, and then it's going to do some planning. You can think of this as a chain of thought kind of an idea. So it's just doing some planning about how to integrate these punchlines into the joke, and then after it integrates these punchlines, then it creates the joke. You see, this is also a form of context engineering, because by explicitly asking it to pick the punchline IDs that it's going to use, we are enforcing the model to think about how we want it to do the task. Because if we did not use this, then the large language model is going to start generating the joke directly without going through these two planning steps. And these two steps really make the language model's trajectory of generating tokens align towards our goal, meaning we want them to use the punchlines that we have fetched for them. Another common way to use RAGs is actually to use it as a memory retrieval system. If you think of memory, there are a couple of different ways to think about it. And I'm going to quickly show some of the common methods, and I'm going to come back with a different video that is entirely dedicated to memory. Let's say you have a simple script like this, which is just a question answering module where you write a question and the AI generates a response. So if you run just this, here you can see the user informs the AI about his name, the AI acknowledges it, and in the next turn when the user asks, the AI says, "I don't know your name." This is because they're using the chat completions API. So by default, it's an isolated transaction. So in the LLM's context, it has no idea about any previous conversations that you may have had with it. So instead, a common way people just inject some memory is by passing in the entire transcript that has happened before into the LLM's context. So for that, the easiest way is to just add this history thing into the input field, which is of type DSPy.history. And as the conversation grows, we just append the user's question as well as the LLM's last answer into the history and then pass it here. So if we run this now, chat1.py, it now recognizes my name. Now, if I run this again without my name, it again has not heard about me. Why? Because we were saving all of the information inside the RAM. So it was only available while the program was still running. Cooler way to do this will be to use some kind of a persistent database. For example, the easiest way to do this is to just include a tool call where you can ask the LLM to write new useful information into a memory file. For example, here's a simple Python tool to just add memories into a memory.md file. In the beginning, the memory.md file is empty. So let's run this thing the first time. It says that user introduced themselves as AVB. And then when we ask, tell me my name, it says your name is AVB. Now, if I quickly look at our memory.md file, you can see that it now has this one entry. Now, what if I ask it the second time and now I don't start the chat with, hi, my name is AVB. And if I run this again, it finds out your name is AVB. which is awesome. Now, maintaining something like this is quite tricky because you need a lot of features to do a proper memory system. For example, you may need to separate memories by different usernames. You may also need to update existing memories. Also, currently, we are passing our entire memory into the prompt, but for long conversations, this might get out of hand. So a better way of managing memory is actually the mem0 system. The mem0 system works in two phases, the extraction phase and the update phase. Basically, mem0 uses tool calls just like we did to save memories into the database. Each memory is also embedded to form a vector representation, which is also saved inside the memory. When the user asks something, mem0 first does semantic retrieval to find relevant memories that are similar to the user's query. It extracts these memories and sends to the LLM to generate a response. And then in the update phase, the LLM can either decide to add, delete, or update the existing memories. And this also happens by doing semantic retrieval and then updating individual memories. Using mem0 is pretty easy. I have a simple script here that I took from the mem0 documentations. You can see that when the user Alice says this, I like to drink coffee in the morning and go for a walk, it creates some memories for the user ID Alice. For example, one memory is likes to go for a walk and the other memory is likes to drink coffee in the morning. You can do a bunch of things with this and marry it with DSPy using tool calls. DSPy themselves have a document on this on how to get started with it. So I urge you to have a look at that. I'm going to leave a link of it in the description. Frankly, the space of using memory into LLM system is advancing at a very brisk pace, and I hope that one day I will create a lengthier tutorial on just how memory systems are evolving in the literature. But till then, I hope you have enjoyed this video and I hope you have been able to learn something from this. In this video, I just used this joke generation example, but you can apply the same principles or the same topics on any project that you are working on. You have to think about what exactly you need to fit into the context, how to create that perfect brain state which contains all the information that the language model needs to generate answers. And it's not just about fitting the context with the right information. It's also about prompting it in a way which encourages the generation in the correct way. For example, how we asked the LLM to cite the references when it was generating jokes. Those things really encourage the language model to follow the pattern that you wanted to follow as a developer, as a designer. Also, we talked about multi-step interactions, multi-agent interactions, different types of agentic flows. We talked about tools, we talked about web search, we talked about RAG and BM25 and all of these things that together forms the ecosystem. And please don't forget about the evaluation parts as well. Observability and monitoring is key, as well as evaluation, because it will tell you if your decisions are right. Like if I find out that the whole DSPy.refine thing is not really useful in generating better jokes, I'll probably just leave it out because maybe it's causing more of a latency issue and eating up more tokens. So all that you can only find out if you write good metrics and do the evaluation ahead of time. Anyway, that's been my time, guys. Again, a lot of this tutorial will be made open source. I'll have a GitHub link below in the description. Our Patreon members will have access to additional code materials as well as all of the slides and documents that went into producing this video. Patreon helps me out a lot. It keeps this channel running. So again, thank you for supporting us over there. All right, guys, that's been my time. I'll see you in the next one.